The other option, of course, is that we could have a situation where fcalc is greater than ftable, where the standard deviations statistically are different from each other. Essentially, what's that saying is that one set of measurements has a very narrow distribution of values, whereas the other one has a very large one, and we can't assume they come from basically the same Gaussian curve. The Gaussian curves are different from each other. We're still going to calculate a t-value and do a comparison to a t-table, but the equation that we use is different. So our t calculated for this case, for this part of case 2, is we still take the difference in the means, the absolute value of it, and we divide it now by the square root of s1 squared divided by n1 plus s2 squared divided by n2. We can also rewrite this just with a slightly different definition and call this u1 squared plus u2 squared, just to make this slightly easier. The other thing is we don't have an S-pool to calculate here, but instead we have to calculate the degrees of freedom. We can't just take n1 plus n2 minus 2 like we would for the other case where fcalc is less than ftable. So the degrees of freedom equation, buckle up for this one, we have s1 squared over n1 plus s2 squared over n2, all of that squared, divided by s1 squared over n1 squared divided by n1 minus 1 plus s2 squared over n2 squared divided by n2 minus 1. We could, again, rewrite this making some differences. Here we have u1, just different definitions here. u1 squared plus u2 squared squared divided by u1 to the 4th over n1 minus 1 plus u2 to the 4th over n2 minus 1. And one key thing to point out here is you will generally not get an integer out of this, whereas of course a degree of freedom is always an integer value, so you'll have to round this to the nearest integer. Okay, so those are the equations. Let's look at how we can apply these to a specific example, which hopefully will help this make more sense.